In this video, we will be discussing continuity and differentiability. So first, we're going to review what is required for a function to be continuous at a given x value. For example, x equals c. The first requirement is that f of c must be defined. So that point is an actual defined point. The second requirement is the limit as x approaches c of f of x must exist. And for the limit to exist, the left-hand limit as x approaches c from the left of f of x must equal the right-hand limit, or the limit as x approaches c from the right of f of x. The third requirement is that requirements 1 and 2 must equal each other. So f of c must equal the limit as x approaches c of f of x. So a quick visual of this situation, say you've got some x value c and some graph that's going along and there's a point. That would be an example of not continuous because there's a hole. But if f of c is defined and the y value of that point is the same as the limit as you approach that point from the left and from the right, then it's a smooth, continuous graph. Today we're going to be discussing what it means for a function to be differentiable at a given x value c. Now the first thing that's required is it has to be continuous. So I should add that on here. F of x must be continuous at x equals c. And the derivative from the left must equal the derivative from the right. So in limit notation, the limit as x approaches c from the left of f prime of x must equal the limit as x approaches c from the right of f prime of x. Now there's three reasons that a function is not differentiable at a given x value. And those three reasons are: if the function is not continuous, it's not differentiable. If the function has a sharp corner or a sharp cusp, it's not differentiable. Or if the function has a vertical tangent line at that x value. So if a function's not continuous, it can't be differentiable. If it has a sharp corner or cusp, the derivative from the left is not going to equal the derivative from the right. If you look at that middle row, these tangent lines from the left and from the right aren't the same. So there's no way to draw a tangent line on a sharp corner or cusp. And then if you have a vertical tangent line on, for example, a cube root, y equals the cube root of x, at the point 0, 0, right here in the middle, there's a vertical tangent line. That graph is not differentiable when x is 0. It is differentiable everywhere else on the graph, so it's differentiable over here, it's differentiable over here, but where there's a vertical tangent line, the derivative is undefined, and therefore the function is not differentiable just at that point when x is 0. Think of, for example, now a quick note about the relationship between continuity and differentiability. If a function is differentiable, that implies that it is also continuous at that point. So differentiable implies continuous because continuity is a requirement for differentiability. If a function is not continuous, that implies that it is not differentiable. But if a function is continuous, that does not imply differentiable. For example, if you have a sharp corner or a cusp, if you have an absolute value graph, y equals the absolute value of x, that looks like a V. This graph is continuous, but it is not differentiable when x equals 0 at that corner point. So continuity does not imply differentiability, but differentiable does imply continuous. Okay, a few examples. So in this first one, it says compare the right hand and left hand derivatives to show that the function is not differentiable at the point P. Okay, so the left hand derivative, if we take the derivative of y equals x squared, we get y prime equals 2x. The right hand derivative, if I take the derivative of y equals x, I get y prime equals 1. So the limit as x approaches 0 from the left of 2x would be 2 times 0, which is 0. The limit as x approaches 0 from the right of 1 would equal 1. And 0 does not equal 1, so the left-hand derivative does not equal the right-hand derivative, and it's not continuous at 0. And if you look at the graph, it looks like coming from the left-hand side, that tangent line looks like it wants to almost be horizontal, but from the right, we get a slope of 1. Okay, next example. At x equals 3, the function is given by f of x equals x squared when x is less than 3, and f of x equals 6x minus 9 when x is greater than or equal to 3. This is a piecewise function, and we want to decide if it's undefined, continuous but not differentiable, differentiable but not continuous, neither continuous nor differentiable, both continuous and differentiable. So the first thing we're going to check for is continuity. So to check for continuity, we need to check first that f of, well, first of all, x squared is continuous on its entire domain because it's a polynomial, and 6x minus 9 is continuous on its entire domain because it's a polynomial. So the point in question is really what's happening at 3, where we switch from one function to another. So we want to see if f of 3 exists. So we plug 3 into this function, and because of the greater than or equal inequality, f of 3 is going to be 3 plugged into that bottom part. 6 times 3 minus 9, 18 minus 9, which is 9. Now we want to check if the limit as x approaches 3 from the left is equal to the limit as x approaches 3 from the right of f of x. Because if so, then the limit as x approaches 3 exists. So the limit as x approaches 3 from the left is what we get when we plug 3 into x squared. So this part is 3 squared, which is 9. The limit as x approaches 3 from the right is going to be plugging 3 into that bottom part. 6 times 3 minus 9, which is 9. So those do equal each other, so the limit as x approaches 3 of f of x does exist. And then the third requirement for continuity is that f of 3 equals the limit as x approaches 3 of f of x, and in this case we got 9 for both of those. So this was 9. So yes, we have all three requirements for continuity. So yes, it's continuous. Yes, continuous. Now the next part is checking for differentiability. So this was part 1. And now I'm going to come over here for part 2. The first thing I want to do is find the derivative of this function. So f prime of x is going to be, and I can just take the derivative of each part. So the derivative of x squared, according to the power rule, is 2x when x is less than 3. And the derivative of 6x minus 9 is just going to be 6 when x is greater than or equal to 3. And now I'm going to investigate if the limit as x approaches 3 from the left of f of x equals question mark, the limit, oh sorry, that should have been f prime of x, the limit as x approaches 3 from the right of f prime of x. The limit as x approaches 3 from the left of f prime of x is going to be plugging 3 into 2x. So 2 times 3, which is 6. And the limit as x approaches 3 from the right of f prime of x is going to be 3 plugged into that bottom derivative, which is just going to be 6. So those do equal each other, the left-hand limit or the left-hand derivative and the right-hand derivative. So that means that this is also differentiable. And so finally, it is continuous and differentiable. And one last example, it says let f be the function given above. What are all values of a and b for which f is differentiable at x equals 1? This is going to involve a system of equations. So the first part is it needs to be continuous. So at 1, we need x plus b to equal ax squared when x equals 1. So that the limit as x approaches f of x from the left equals the limit as x approaches f of x from the right. And that will be the same as f of 1. So I plug in 1 for x, and I simplify as much as I can. And so I get 1 plus b equals a. Now the second requirement is that this function is differentiable. So this was the continuous part. And now we're going to do the differentiable part. And so we need to find f prime of x, which is going to be, if I take the derivative of the top, I'm just going to get, well, the derivative of x is 1, and then b is a constant, so that part goes away when x is less than or equal to 1. And then the derivative of ax squared is going to be 2ax when x is greater than 1. And we need to equal those, we need to set those two equal at when x is 1. So we need 1 to equal 2ax when x equals 1, so that the derivative from the left is equal to the derivative from the right. And so I plug in 1 for x, and I get 1 equals 2a times 1, or 1 equals 2a. So this part is my differentiable step. And now, for both of these things to be true, I'm going to have to solve a system of equations using this equation and that equation. So the system of equations is going to be 1 plus b equals a, and 1 equals 2a. And so we solve. I'm going to use substitution, I guess. I can get a by itself pretty easily if I divide both sides by 2. Then I get 1/2 equals a. And then I can substitute that into the equation on the top and get 1 plus b equals 1/2. And then if I subtract 1 from both sides, I get b equals negative 1/2. And if I look at my answer choices, a equals 1/2 and b equals negative 1/2 is my first answer choice.